Hello and welcome back. We are discussing section 2.3. In particular, we are discussing the quotient rule, the second part of this learning objective, and then we'll also try to tackle second and third derivatives. So, where there is multiplication, there is often also division. So we discussed the product rule, which dealt with the derivative of two components getting multiplied together, each of which involving some variables. So now we're tackling quotient rule, which is basically the same structure. We've got two functions, things with x's in them. That's all that we really care about. They need to be differentiable, so their derivative needs to exist because the derivative of their ratio, f of x over g of x, involves f prime and g prime together. So there is one piece of good news, and that is, if you notice, everything on top here should look fairly familiar with respect to product rule. All the terms come in the same order. We've basically structured it so that that's the case. And then the only catch is that this is positive. It's an addition sign for product rule. So in the quotient rule, they're the same terms involved, but for product rule, there's addition between them. And for quotient rule, we've got some subtraction. And then, of course, a major notable difference is that we've got a fraction here as well. We're actually dividing by some interesting stuff. So just the same reminder for quotient rule as there was for the product rule. Unfortunately, if I take stuff on top and stuff on bottom and I want the rate of change in that whole fraction, it's not f prime over g prime. As much as I would like it to be, that doesn't describe the rate of change appropriately. So we'll just jump right in with a word problem, because that's what everybody loves so much anyway. So we'll take a population model for deer, we'll take t in years, and we'll say the population is p of t given by this expression. So 2 plus 3t on top, 5 plus 3t on bottom. And this is supposed to represent not just total population, but a fraction of the carrying capacity. So we're going to get a decimal out of this somehow. And ideally a decimal between 0 and 1, although in theory we could be temporarily above a carrying capacity, for instance. So there's just a reminder here saying, oh look, if we plugged in 0, you would see that the deer population is at 40% of its capacity. Okay, our job is to, this typical phrase, find and interpret. So the mathematical part is the finding piece, and the interpreting portion is some sort of statement at the end. And it's our job to do this for p prime of 1. And as before, that prime just means take the derivative of this population function, in this case, and then plug in 1 for all of the t's. So here we go. I guess the first thing to note is that it really does follow this format for quotient rule. We have on top has t's in it, on bottom we've also got t's. There's no great algebraic way to tidy this up. So the best way to ask for the rate of change in this whole thing is to use quotient rule. So there's a kind of, I don't know, I'll call it dumb because it does feel kind of dumb, but a little mnemonic to go along with this quotient rule to help us remember. But recall that for our class, you're going to have a note card whenever it matters anyway. All of your exams you get to have a note card, so if you want to write quotient rule on that note card, then feel free to do so. So memorizing isn't really all that critical. But the mnemonic that goes along with this is low d high minus high d low. So the low piece is remarking on the fact that this is the bottom piece of the fraction, 5 plus 3t. And then d high says the derivative of the top, that's the d piece, derivative of 2 plus 3t. So low d high minus high d low. So there is a payoff here, a trade-off, if you will, because in order to make this look like product rule, we have to write it in this order with the derivative thing first, but the little rhyme that goes with this has low first, low d high minus high d low, and then square the bottom, and away we go is how the little rhyme finishes off. But that's to help remind you that d low should be the second thing in our subtraction. It actually does matter. Unlike product rule, it does matter what order we put these terms on top in, because if we subtract in the other order, we're going to get the negative of what we really want. Okay, so we've taken one big derivative, this big fraction, and turned it into two smaller ones, derivative of 2 plus 3t and the derivative of 5 plus 3t. Those are both pretty manageable. So derivative of 2 plus 3t is 3, and the derivative of 5 plus 3t is also 3. So those were the two derivative pieces that were in the previous slide went to. So you notice there are no more derivative instructions here. We accomplished all of those. So all that's potentially even left to us is some algebra. And if we do that, we do a little distribution. We've got 15 and minus 6. We've got a constant term of 9. And then with the variable stuff, we've got 9t. But then we take away 9t as well. So actually all we have left in the numerator is that 9. And on the bottom, applying the laziness principle, let's just say, if I don't have to multiply this out, why would I? It doesn't really simplify anything or make my answer any tidier. So I'll just leave 5 plus 3t squared exactly where it is. But so we've found, but we haven't actually plugged in a value for this derivative. We found the derivative function, so now we're going to take t is equal to 1, and we get 9/64. So that's an approximation, but 0.1406. And keep in mind that this is not an actual population. This is a fraction of the carrying capacity. So our interpretation is going to have to involve that piece of it. Okay, so input is in years, output's a fraction of carrying capacity. So here's our interpretation. After 1 year, so that's just using this input piece. I'm going to try to make sure that the interpretation covers all aspects of this p prime thing. So the 1 we tackled, that's 1 year. P prime itself is a rate of change. So this is the population is growing at a rate of, and then what it's actually equal to is this value, about 0.46. And then the units on this always look like units of output divided by input. So percent is the units on output, and percent of carrying capacity specifically, and then the units on input are years. So our derivative has units of output divided by input, percent of carrying capacity per year. So 1 year into this study, the population is growing. We would expect in the next year to grow about 14% of its toward its carrying capacity. So the quotient rule is tackled. That's another thing we can put in our toolbox. Product rule, quotient rule, power rule are all part of our way of determining that, derivatives at this point, the derivative functions. And so now that we've mastered that, that's sarcasm, we can start talking about so-called higher order derivatives. So the first stop on that way is to talk about the second derivative. And before you start getting too scared about this, there's no new rules, there's nothing fancy about a second derivative. It just says you start with the derivative and you take the derivative again. So the first derivative, or what we typically just call the derivative, would look like f prime of x. So the second derivative just has an extra prime. The Leibniz notation for this is a little worse. What used to be dy dx, just for the derivative, now has these squares on here to indicate that it's the second derivative. Try not to use this notation too much because it really is pretty gnarly. So what the second derivative is supposed to be telling us about is how the rate of change in the derivative is going. So in other words, if we look at the slope, which is the derivative of some function, how are those slopes changing as we increase our input? So, and we'll get more to interpretation as we move along, but as far as computation, it's actually nothing new. So, okay, one little stop off on the way. So if we want more than a second derivative, we wanted a third derivative, a fourth derivative, etc., then the notation I guess I'll just say, I'm probably never going to give you something past the third derivative, so we don't really have to worry about this notation. But if we were to write a fourth derivative here, then once we get past 3, we start using this notation with a little parentheses for the exponent. So it's not really an exponent, but f to the, and then with a little 4 inside parentheses says the fourth derivative of some function. Yeah, so this starts to get a little awkward, but interpretations are hard to come by for these higher order derivatives, but actually the computation is really nothing new. We don't need new rules to compute second, third, fourth derivatives. All right, as usual, this doesn't really make any sense until we try it on an example, so let's see if we can do that. So here's our revenue example. We'll just steal it back from earlier example from the product rule. And instead of just computing r prime, we're going to go for r double prime. We're going to interpret it as well, so that's going to take a moment. And then our triple prime, notice there's no interpret piece of that, since it's a little bit harder to come up with interpretations for those. All right, so here's our revenue. And from example 2, we already computed the first derivative of that. So we used our power rule along with product rule and got this derivative. So all that's left to us is to figure out the derivative of this thing. So we start with r prime, and then we take its derivative. And I feel like the best way to approach this psychologically is just to sort of pretend that we started with this function originally. You can just use one of those like Men in Black brain eraser devices and say, okay, let's just pretend this is the starting function. I really just want the derivative of this. And I'm ignoring the fact that there's already a prime here. It's already the derivative of some other function. So if I just think, look, all I have is 12 minus 2p minus 3p squared, I'm pretty good at taking the derivative of something like that. And that's our entire task. So with some power rule, the 12 is out of the picture, derivative of negative 2p is negative 2, and the derivative of negative 3p squared is negative 6p. So this is the second derivative of revenue. We're supposed to plug in a value, so let's let p equal 1 in this case, and the second derivative is negative 8 once we plug that in. So let's figure out units because we're going to need to trace through this interpretation, and part of that is going to be getting units right. So if we plug in 1 for r prime, we know that revenue is increasing there. This is part of our previous example as well. So if we plug in 1 to the derivative function, we get all the way through, we get 7. And remember that our output on revenue was in hundreds of thousands of dollars, excuse me. So we've got unit price of $100 per phone, and that's sort of what helped lead us to larger units of revenue, but we'll get there. So revenue is increasing. That's the short answer. But this is not a statement about r prime yet, or not a statement about r double prime, the second derivative. This is just a statement about r prime. So what we also know is that r double prime, this is supposed to tell me the rate of change in marginal revenue, if you will. So not just how revenue is changing, but how is the change in revenue changing. So this derivative, this second derivative, is a negative number, and that's supposed to tell me that the derivative itself is decreasing. So r double prime says that this marginal revenue thing is headed down. So for a complete interpretation, we could say something like the following. When we get close to this input, so near a unit price of $100 per phone, there's our input value, p equals 1. Rate of change is positive. That's a result from the derivative. Rate of change in revenue, r prime, but it's decreasing. So revenue is headed upwards, but the slopes are getting smaller. So one way we could think of this is that if we looked at the revenue graph, it would be curved downward, and we would be on the upward part of that swing. So we're headed upward, but less so as time goes on. So this is a positive first derivative, but a negative second derivative because those slopes are getting less and less shallow, or less and less steep as we go along. Okay, so we did have a second piece of this. We don't have to do any interpretation, so we're supposed to find the third derivative of r. So we start with the second derivative function, and again, we try to do one of those brain eraser things and just say, look, if I start with this as my function, what would its derivative be? So r triple prime starts with the derivative we had just a moment ago and takes its rate of change. So this doesn't involve anything fancy either. This is some power rule. So derivative of negative 2 is 0. Derivative of negative 6p is negative 6, so boom, there's our derivative. It's a constant. And then that's all we really needed to answer this question. But one final note for this, if we wanted to compute a higher derivative, if we tried to figure out what what r with a fourth exponent would be, so the fourth derivative, then no matter what we were looking at beyond 3, the fourth derivative, fifth derivative, sixth derivative, these would all be 0. And that's just because we started with a constant here. And the derivative of a constant is 0. And then every other step along the way, you'd be starting with the previous thing, starting with 0, taking its derivative. That's just going to give you 0 all the way down the line. So even though they didn't ask us to figure out the fourth, fifth, sixth, etc., any of those answers we could figure out immediately and just say, oh, there's 0 for this revenue function. Okay, so that's it for section 2.3. Luckily, it kept us under 15 minutes, but thanks for sticking with it.